In mathematics and signal processing, the Z transform converts a discrete-time signal, which is a sequence of real or complex numbers, into a complex frequency domain representation. It can be considered as a discrete-time equivalent of the Laplace transform. This similarity is explored in the theory of timescale calculus. History. The basic idea now known as the Z transform was known to Laplace, and reintroduced in 1947 by W. Hurewicz as a tractable way to solve linear, constant coefficient difference equations. It was later dubbed the Z transform by Ragazzini and Zada in the Sample Data Control Group at Columbia University in 1952. The modified or advanced Z transform was later developed and popularized by E.I. Jury. The idea contained within the Z transform is also known in mathematical literature as the method of generating functions, which can be traced back as early as 1730 when it was introduced by de Moivre in conjunction with probability theory. From a mathematical view, the Z transform can also be viewed as a Laurent series, where one views the sequence of numbers under consideration as the expansion of an analytic function. Definition. The Z transform, like many integral transforms, can be defined as either a one-sided or two-sided transform. Bilateral Z transform. The bilateral or two-sided Z transform of a discrete-time signal x n is the formal power series 10 defined as where n is an integer and z is, in general, a complex number, where a is the magnitude of z, j is the imaginary unit, and is the complex argument in radians. Unilateral Z transform. Alternatively, in cases where x n is defined only for n0, the single-sided or unilateral Z transform is defined as in signal processing. This definition can be used to evaluate the Z transform of the unit impulse response of a discrete-time causal system. An important example of the unilateral Z transform is the probability generating function, where the component x n is the probability that a discrete random variable takes the value n, and the function x is usually written as x in terms of s equals z minus 1. The properties of Z transforms have useful interpretations in the context of probability theory. Geophysical definition. In geophysics, the usual definition for the Z transform is a power series in Z as opposed to Z minus 1. This convention is used, for example, by Robinson and Treitel and by Knazewicze. The geophysical definition is the two definitions are equivalent, however, the difference results in a number of changes. For example, the location of zeros and poles move from inside the unit circle using one definition, to outside the unit circle using the other definition. Thus, care is required to note which definition is being used by a particular author. Inverse Z transform. The inverse Z transform is where C is a counterclockwise closed path encircling the origin and entirely in the region of convergence. In the case where the rock is causal, this means the path C must encircle all of the poles of X. A special case of this contour integral occurs when C is the unit circle is stable, i.e., all the poles are within the unit circle. The inverse Z transform simplifies to the inverse discrete-time Fourier transform. The Z transform with a finite range of n and a finite number of uniformly spaced Z values can be computed efficiently via Bluestein's FFT algorithm. The discrete-time Fourier transform, not to be confused with the discrete Fourier transform, is a special case of such a Z transform obtained by restricting Z to lie on the unit circle. Region of convergence. The region of convergence is the set of points in the complex plane for which the Z transform summation converges. Example 1. Let x n equals n. Expanding x n on the interval it becomes looking at the sum, therefore, there are no values of Z that satisfy this condition. Example 2. Let Expanding xn on the interval it becomes looking at the sum. The last equality arises from the infinite geometric series, and the equality only holds if 0.5 z minus 1 less than 1, which can be rewritten in terms of z as z greater than 0.5. Thus, the rock is z greater than 0.5. In this case, the rock is the complex plane with a disk of radius 0.5 at the origin, punched out. Example 3. Let expanding xn on the interval it becomes looking at the sum using the infinite geometric series. Again, the equality only holds if 0.5 minus 1 z less than 1, which can be rewritten in terms of z as z less than 0.5. Thus, the rock is z less than 0.5. In this case, the rock is a disk centered at the origin and of radius 0.5. What differentiates this example from the previous example is only the rock. This is intentional to demonstrate that the transform result alone is insufficient. Examples. Conclusion. Examples 2 and 3 clearly show that the Z transform X of xn is unique when and only when specifying the rock. Creating the pole zero plot for the causal and anti-causal case show that the rock for either case does not include the pole that is at 0.5. This extends to cases with multiple poles. The rock will never contain poles. In example 2, the causal system yields an rock that includes z equals infinity, while the anti-causal system in example 3 yields an rock that includes z equals 0. In systems with multiple poles it is possible to have an rock that includes neither z equals infinity nor z equals 0. The rock creates a circular band, for example, has poles at 0.5 and 0.75. The rock will be 0.5 less than z less than 0.75, which includes neither the origin nor infinity. Such a system is called a mixed causality system, as it contains a causal term n and an anti-causal term -n minus n minus 1. The stability of a system can also be determined by knowing the rock alone. If the rock contains the unit circle, then the system is stable. In the above systems, the causal system is stable because z greater than 0.5 contains the unit circle. If you are provided a Z transform of a system without an rock, you can determine a unique xn, provided you desire the following: stability, causality. If you need stability, then the rock must contain the unit circle. If you need a causal system, then the rock must contain infinity and the system function will be a right-sided sequence. If you need an anti-causal system, then the rock must contain the origin and the system function will be a left-sided sequence. If you need both stability and causality, all the poles of the system function must be inside the unit circle. The unique xn can then be found. Properties. Parseval's theorem. Initial value theorem. If xn is causal, then final value theorem. If the poles of x are inside the unit circle, then table of common Z transform pairs. Here is the unit step function and is the discrete-time unit impulse function. The two functions are chosen together so that the unit step function is the accumulation of the unit impulse function. Relationship to Fourier series and Fourier transform. For values of z in the region z equals 1, known as the unit circle, we can express the transform as a function of a single, real variable, omega, by defining z equals ej omega. And the bilateral transform reduces to a Fourier series, which is also known as the discrete-time Fourier transform of the xn sequence. This 2π periodic function is the periodic summation of the Fourier transform, which makes it a widely used analysis tool. To understand this, let x be the Fourier transform of any function, x, whose samples at some interval, t, equal the xn sequence. Then the dtft of the xn sequence can be written as, when t has units of seconds, has units of hertz. Comparison of the two series reveals that is a normalized frequency with units of radians per sample. The value omega equals 2 pi corresponds to Hz. And now, with the substitution EQ, one can be expressed in terms of the Fourier transform. When sequence X represents the impulse response of an LTI system, these functions are also known as its frequency response. When the X sequence is periodic, its DTFT is divergent at one or more harmonic frequencies, and zero at all other frequencies. This is often represented by the use of amplitude-varying Dirac delta functions at the harmonic frequencies. Due to periodicity, there are only a finite number of unique amplitudes, which are readily computed by the much simpler discrete Fourier transform. Relationship to Laplace transform. Bilinear transform. The bilinear transform can be used to convert continuous time filters into discrete time filters, and vice versa. The following substitution is used to convert some function in the Laplace domain to a function in the Z domain, or from the Z domain to the Laplace domain. Through the bilinear transformation, the complex S-plane is mapped to the complex Z-plane. While this mapping is nonlinear, it is useful in that it maps the entire j-omega axis of the S-plane onto the unit circle in the Z-plane. As such, the Fourier transform becomes the discrete-time Fourier transform. This assumes that the Fourier transform exists, i.e., that the j-omega axis is in the region of convergence of the Laplace transform. Starred transform. Given a one-sided Z transform, X, of a time-sampled function, the corresponding starred transform produces a Laplace transform and restores the dependence on sampling parameter. The inverse Laplace transform is a mathematical abstraction known as an impulse-sampled function. Linear constant coefficient difference equation. The linear constant coefficient difference equation is a representation for a linear system based on the autoregressive moving average equation. Both sides of the above equation can be divided by alpha 0, if it is not 0. Normalizing alpha 0 equals 1 and the LCCD equation can be written. This form of the LCCD equation is favorable to make it more explicit that the current output Yn is a function of past outputs Yn minus p, current input Xn, and previous inputs Xn minus q. Transfer function taking the Z transform of the above equation yields and rearranging results in zeros and poles from the fundamental theorem of algebra. The numerator has m roots and the denominator has n roots. Rewriting the transfer function in terms of poles and zeros, where qk is the kth0 and pk is the kth pole. The zeros and poles are commonly complex, and when plotted on the complex plane it is called the pole zero plot. In addition, there may also exist zeros and poles at z equals 0 and z equals infinity. If we take these poles and zeros as well as multiple order zeros and poles into consideration, the number of zeros and poles are always equal. By factoring the denominator, partial fraction decomposition can be used, which can then be transformed back to the time domain. Doing so would result in the impulse response and the linear constant coefficient difference equation of the system. Output response. If such a system H is driven by a signal X, then the output is Y equals Hx. By performing partial fraction decomposition on Y and then taking the inverse Z transform, the output Yn can be found. In practice, it is often useful to fractionally decompose before multiplying that quantity by Z to generate a form of Y which has terms with easily computable inverse Z transforms.